Okay, welcome you all to today's lecture on advanced remote sensing techniques for geological hazards with emphasis on landslides. I hope you are enjoying the course, and I have two consecutive lectures. One is on the geological hazards, emphasis on landslide, another was on engineering geology. So the first lecture is dedicated to this. So as you know, as for the geological hazards are, as far as that are concerned, we need to understand first few definitions. What hazard is, what disaster is, the vulnerability, susceptibility, risk. These three components are to be clearly understood. So I'll start with the vulnerability part. Vulnerability is basically that is element specific, and it is the capacity of the social, physical and economic structures taken together to withstand any kind of hazard. Susceptibility on the other hand is the capacity of the vulnerable elements to withstand and action a given degree of severity at a particular spatial connotation in a particular time. So from this we understand that vulnerability is basically element specific. We have to have elements which are at stake, basically like your social, physical and economic. It can be simply, suppose we take the building layers, building footprints, we can take the cropland, the agricultural lands, like this, and the roads. Susceptibility on the other hand, we have to take all the thematic layers, we call it thematic layers, which basically makes the area susceptible. Like for today we are going to see it in the context of landslides. So landslide susceptibility will mean the potential of landslide in a particular area with respect to slope, the geology, lithology, structure, geomorphology, distance to river, distance to fault line, seismicity of that area. All these taken together will give me what is called susceptibility. Vulnerability simply is the layers that are at stake, we take them together to get the vulnerability. Now risk, the third term that we need to understand. Risk is basically defined as expected loss due to the hazard in a particular area. So in this case, the risk basically takes care of the susceptibility part and the vulnerability part. So susceptibility crossed with vulnerability will give me the risk. But obviously, as we understand, the risk should not only consider the susceptibility and vulnerability. There are many more things that are also to be considered. Risk of an area, suppose you prepared a risk map. How we prepared that we are going to learn in this lecture. So how we are going to make this will come first, but what are the things that we take? We take the susceptibility, we take the vulnerability. Apart from that, it will be a nice idea if we take the factor of safety. So that is basically resisting force by the driving forces. So that basically says how competent your buildings are. So this factor is required to understand how strong my buildings are. So this is basically a strength parameter of the building. Beside this, we can take care of the social factor, the exposure, we call it exposure, that is related to the financial condition, suppose the economic condition, how many people are there, the ethnicity, where they are living, rural area, urban area, in which condition. So this is basically the exposure. So exposure and the factor of safety is something that we are keeping out from this discussion. We are taking care only of susceptibility and vulnerability. Risk assessment is something that we are going to understand, we are going to learn in this lecture. So to start with the landslide part, we very commonly see in newspapers, news channels and comment that landslide has occurred there. It's not that a landslide is a single term, it constitutes of so many things together. If you see this diagram, the classification of landslide lies here. So here, this axis, we see the type of the material involved. It can be rock, can be debris, can be earth. Earth means nothing but soil or mud. And this vertical axis is the process involved. So by process, I mean it is simply fall. So rock falls, suppose the granules of rock, fragments of rock that falls, then debris falls, then earth falls. So obviously earth and debris falls, something like that doesn't occur that common. But rock fall is quite common. Next is topple. So difference between The fall and the topple is that, you please understand, the topple has to happen along the discontinuity plane, or it can be a bedding surface, can be a joint, can be a fault line, can be a shear zone, shear plane, anything. So these discontinuities, basically along these discontinuities, the beds get detached and they flow downward, they topple downward due to influence of gravity. So there is rock topple, debris topple and earth topple. Earth and rock debris topple are slightly less common than your rock topple. Then comes the sensu stricto slides. So slides again can be divided in two terms, that is, one is rotational, another is translational. So rotational slides, very clearly you can understand that where the failure surface, we call it failure surface. What do you mean by failure surface? It is basically the surface that separates the top weathered mass and the bedrock down there. So obvious, it is quite obvious that this top weathered material is going to get dislodged due to influence of gravity because of a trigger. Suppose the trigger can be rainfall, can be seismicity, earthquakes, and the material goes down. So, but the failure surface is carved, remains to be a carved one. Here the failure surface is there, but that is a straight planar surface. This is the difference between a rotational and a translational slide. So that can be debris, that can be earth also, with earth also. Spreads, on the other hand, is the fourth thing to learn. Spread is simply your material is spreading on the surface. There can be mud or earth spread, there can be rock spread, is slightly uncommon. Again, because rock just like that cannot spread. Then come the flows. One thing we need to understand, that the more we come down in this axis, the mechanism wise, then the more water is involved. So fall, topple, slides, they were drier phases, but this spread flow onwards, they are quite wet, so that means water is there. In case of flows, lot many water is there, and rock flow, debris flow, mud flow, all three are common, but debris and mud flow, they are the real culprits. So here in this phase, these are the processes that were dominant. Here they are basically dominant, where your fine grained material are more involved. Then comes the complex. Anyhow, we need to understand it. Any big landslide is not that only one type it will have. It can possess two or more types of mechanisms involved. So suppose top, we have a top layer, or the source zone, we have a rock fall, and down there we have a debris flow. So that basically is a complex. Any big landslide on earth shows is basically a complex only, where more than one mechanism are involved. Now if we want to understand landslides from an earth observation point of view, so that means we will go to the field, collect samples, but before that we have to see the satellite images to look for the landslide, to understand them, to analyze them. So what are the different stages involved in landslide studies when we are going to use remote sensing data, satellite based products, or satellite images as such? So first thing that you should move with is the inventory map. Inventory is nothing but the active landslide polygons that you mark on a GIS layer. You can do it on, suppose, Google Earth images also. Mark the landslide polygons with KMZ, KML files, or in ArcGIS or GIS software you got the .shp save files saved as that. So those active polygons will be my inventory layer. The inventory layers are something like is utterly important, because if you go by the old saying by James Hutton that present is the key to the past, that basically means that what is happening today have been happening in yesterday also, and future also it may happen. So if I make an inventory today, that simply means that the area where more landslide active polygons are concentrated, they will be the areas that we look for further more landslides. In future also we should look in these areas only. So that's why we create an inventory, and how the inventory, it's not just for the sake of the creation only. We have to use this layer later on. We will learn how to use this. Then comes the vulnerability aspect and susceptibility aspect. So the moment you come to vulnerability and susceptibility, you are basically assessing the landslide. So it comes to assessment. Inventory was more of monitoring. Then The next stage will be the evaluating risk of that. So that is basically assessment come mitigation. So you are now on to the mitigation the moment you calculate risk, and suppose you further model your slides. So for predictive modeling, suppose if you simulate a landslide and see then how in future that is going to behave, you are really in the field of mitigation. So that is this slide basically shows you the stages of landslides and what status are involved associated with that. Now I will start with the result part, what we basically get with this kind of mapping using remote sensing GIS. So the result is something that we show you first, and then step by step I will show you how to get this kind of result. So this is your result in front of you that shows the landslide hazard map along the road corridor. It has been prepared for the famous Hindu shrine called Kedarnath, and this map was prepared by IIRS with the help of NRSC somewhere in early 2000 or late 99, 98, like that. So they basically show you where the very severe, very high, very low, moderate zones of susceptibility or hazard lies. So this hazard class, hazards just like that, it simply means that it's susceptibility only. So landslide susceptibility you can call it. And please see, this is the Kedarnath temple. You probably all of you are aware of what happened in 2013 Kedarnath event. A major flash flood kind of thing happened, and lot many landslides happened, and as per the government news, there were around 5,000 at least life loss associated with this particular event. So that is how it requires further studies. We have newer case studies also that I will present here today only. But this old map also, please understand, in the vicinity of Kedarnath there are so many very high severe zones already involved. So it has remained to be a hotspot for landslide occurrence since suppose 20-30 years back also. So it's not new. So that this kind of map is something that we will produce at the end of this. We'll understand how to produce it at the end of the lecture. So what are the materials involved? What you basically required to start with? Suppose after this lecture you are inspired to make a susceptibility or a vulnerability map or a risk map. Then what are the layers? What are the inputs that are required for this? Let us understand one by one. First is, I've told you, first thing is your inventory map. For inventory, you have to have polygons, active landslide polygons. You can make it free images available on Google Earth platform, or you can use IIRS data, Indian Remote Sensing Satellite data, or you can use any high resolution satellite image that is available. That is not open source. You can purchase it. So all the sources will tell you where your landslides are acting. So that basically gives you, if you prepare that on a GIS layer, suppose with the softwares like ArcGIS or QGIS, you get an inventory map. Next comes your suppose vulnerability map, the last one. Vulnerability, for that we'll take settlement, we take the road, we take the agricultural field, all these layers taken together and stitched together, added together. If we think like we can further put weights to them, so that basically gives me the vulnerability map. And for susceptibility, I have taken here slope, aspect, relative relief, geology, stream, land use, land cover, etc., etc. All these layers further weighted together gives me susceptibility mapping. So now the point is that how do I stitch this? The moment I say that I add them upon one another, juxtapose them together. So how do I do that? There are different algorithms, mathematical algorithms involved, where people have explained how this addition is to be, union is to be done. So one way, is simply by suppose I am completely unaware about the study area, and the operator is doing from a remote place. He is not conversant about the area as such. So what he will do, he will go for all the mathematical and statistical models involved based on pure mathematics. So whatever the mathematics algorithms, how they will feel like, all your input layers will be handled that way, and the final output you will get. Another way is that you go knowledge based or heuristic methods. Heuristic methods are simply that where operator has ample knowledge about the study area. He or she can tell that no, out of these suppose 10 layers, slope to geomorphology, out of these 10-12 layers, which one are the most important, which one are to be kept, which can be excluded also, because like I can add upon more layers, I can exclude many layers, but this has to be done with a cautious, because if I miss any important layer, my final map is something that will be wrong. So that's what I have to be cautious in selection of these layers. Again, addition of layers at times may dilute the algorithm, and the results also may not come true. So that's why you have to be real cautious. So for sustainability, suppose 10 layers I have to play with, and I can apply as with my prior knowledge, I apply more weights to slope or aspect, or suppose geology, I understand that lithology is the main culprit here. Okay, so I give more weight to the lithology component, like that. So once you give weights, you can bind them together. So that is one way. Another third way is that you are partially conversant about the area, you do not completely know about the area. So you need to adopt a model which is partially mathematics based, partially knowledge based. So the mixed models are also available. Next, for debris flow modeling, we will see that how it is done. For that, what are the inputs are there. The input is basically some topographic information, and you need to have a good quality DEM, digital elevation model. I hope people understand what DEM is basically the 3D. So the association of XYZ points, and then you plot, you get the suppose the 3D, that is a representative of DEM, digital elevation model. So for this kind of flow modeling, where predictive modeling is to be done, you need to have the DEM to start with. Now, one method only I have described here, the way mathematically or semi heuristic way it can be done. Please understand, we have these layers involved: distance to stream, relative height, slope, aspect, vegetation, soil depth, etc., etc. All these layers, each of these layers are called raster thematic maps, because they represent, each one of them represent one theme. So that is why they are called thematic maps. Now the thematic maps will have classes within them. Suppose we take the slope map, and within this we have suppose 4 classes: 0 to 30 degree, 30 to 60 degree, 60 to 75, 75 to 90. 4 classes are there. So each of these maps will have different classes within it, suppose 4 or 5 classes each. So what I have to do next, what I want to make you understand, is that you bring your inventory layer and juxtapose the inventory layer on each of these thematic layers. So what is happening here, suppose I am superposing my inventory layer on a slope layer and ask the software to unite it. So basically the resultant map, what you will see, the slope map within each of the classes, 4 classes it had. So each of the classes, how many polygons of landslide or how many pixels of landslide it is having. So basically it tells you the classes, each class of that raster thematic map, how many landslide polygons are there. In turn, this basically gives me information about how important that class is in terms of landslide initiation. Suppose I get 75 to 90 degree class, this is where maximum of the landslide polygons, active landslide polygons, are falling upon. So that simply means that that particular has something to do with the landslide occurrence. So that is how you you get a glimpse of what is happening there. In each of these thematic layer, the maximum concentration of landslide polygon is going in which class. So that class is the culprit, or maybe the reason behind the landslide triggers. So what I have done, I have juxtaposed the inventory layer on each of these layers separately. Now I get a separate map for as a result from all these. Now, those maps are to be further weighted. The algorithm that has been applied here, that basically gives me information value of the weighted maps. What are the weighted maps? Basically we have juxtaposed that layer, each layer with inventory layer. Now I play with the algorithm within the software. It is called information value method. So for each of the pixel, of the thematic raster layer, I have each pixel I have one information value. Rather, on an average for each of the class, I take the information value. So information value is directly related to how many landslide pixels were falling on that particular class. So the information value is more positive, that means more landslides are there, so the class is more akin to occurrence of landslide. If it is less than 1, that means it doesn't have as such influence on landslide incidence. So here comes the weighted factor maps, one layer weighted maps. Again they will be clubbed together to get a map like this. So please understand, each of these pixels, each pixel in this map, what does it connote? It connotes information about this layer, information about height, slope, comma aspect, comma vegetation, comma soil depth, comma landslide, yes or no, bracket close. So each pixel has these many information. I asked the software to classify this, so wherever it gets similar values of information, so it basically clubs them together and gets me different zones. So red zone basically indicates where high, all pixels with high information value are associated. So that basically gives me a zone, very high zone, and green obviously indicate a less stable, very low zone. So there are classification like very high to very low, 5 classes is generally what we take. On the contrary, I suppose I take the build up, I take the road, I take the agricultural field, and again stitch them together, giving individual weights to them based on our prior knowledge. I get a susceptibility map. So vulnerability map. So vulnerability map and susceptibility map, if I cross this together, is what I get as a risk map. So risk map, each pixel, what does it tell you? It tells you within bracket in value of susceptibility, comma value of vulnerability, bracket close, then classified. So similar classes, high risk will be my red and low risk will be my green, like that. So there is a basic methodology involved. Then landslide inventory. So on suppose satellite image, or here I have taken from Google Earth only, we try to get the polygons. Yellow ones are the polygons here, and how they are draped on the 3D, and what you can see here is the landslide polygon. So this is the village called Ukimat, and the village basically is infested with your landslide polygons. Coming to the vulnerability, I have the building footprint. So you prepare a building map, you prepare a road map. The beauty of the roads in hilly areas is that if something happens here and landslide goes like this, so one same road, single road is averted by the landslide at many places, and your traffic will be disrupted. So taking this in consideration, we need to understand the road is of utmost importance in terms of vulnerability mapping. Then the agricultural field, they can be destroyed, it can be school, it can be cattle shed, it can be anything. So according to your choice, you take your own vulnerable elements, map those, and like this you get a settlement, you get a road, you get agricultural land, you add these layers together to get a vulnerability map like this, where very low to very high classes are there involved there. Susceptibility, we take the geomorphology, stream distance, fault distance, etc. all the 12 layers together. Suppose you can add more, you can even exclude some of the layers, and please see there are your classes are involved in each of these. So each class will finally, each class is going to give me one information value as per the method I have applied here. So this is what it shows. So each of these bars, color bars, basically represent the classes. The classes from each of the thematic layers. So very high values are earmarked, so that simply indicates they are the classes which coincide with landslide occurrence. So they are basically influential, a kind of influential in landslide occurrence, and negative classes are also there. So I get this kind of map, susceptibility map. Susceptibility map, in general there is ambiguity about these terms. So some people equate susceptibility with the hazard. So the moment I say it is a hazard map, you can ask him that is it a susceptibility map or you are referring to a risk map? Because if you have the vulnerability map, So if you have the vulnerability map, you have the susceptibility map, you get a risk map as well separately. So if it is hazard, in all probable cases it will basically be the susceptibility only. If not, the author is speaking about a separate risk map. Right, so side by side, if I portray, it will look like this. So vulnerability, susceptibility and risk. One thing I would like to remind here is that the risk is a union of cross product of these two. So any high risk zone, for any high risk a pixel, if it has to be high risk, that simply means that the vulnerability value at that pixel and the susceptibility value at that pixel both simultaneously have to be high. It's not that one of them can be low. On the contrary, if the risk is low at any pixel, that simply means that either of susceptibility or vulnerability or both are low. So that's why high risk mean the areas, the red areas where susceptibility is there. At the same time, we are having important elements like your buildings, like the elements are also present. So that is what a risk map is. Similar studies had been done in Yamunotri area. Yamunotri is another Hindu shrine among the Char Dham of Uttarakhand, and we could produce the very low to very high classes just to see that if I juxtapose the road layer on this, and wherever the road basically passes through your red zones, they are the areas where the government is to be alerted, or the people also have to be cautious while passing through that. They are high hazard zones. That means they have potential for landslides occurring there. So they need to be cautious, alert. Kedarnath is something that we have worked vigorously. Pre-Kedarnath image we have seen pre-event, and post-event also, I mean post-2000 event also we have done, and we have prepared vulnerability and risk maps. And still even after the event, the temple area and adjoining places, they pose quite a high risk. Now coming to the second half of this lecture, which is dedicated to the last part where the mitigation was to be done. So for that, okay, I am done with the susceptibility layer, so or risk layer, and I know that which are the areas where the high risk zone is there. So that simply indicates that I have to avoid those areas. But it happens like that I cannot just like that avoid the place. My house is there and I have to be there only. But how then the slide can be averted? Obviously it's a landslide is a natural process. So like any natural process it will happen. But how the risk of getting my house's life damage, that can be reduced, that is something to be thought of. So that is how the most culprit, notorious event that happens in Uttarakhand Himalaya is the debris flow component. It's type of landslide where it's a rainfall triggered debris. Debris is a mixture of rock and soil plus water. So that suddenly goes down under the influence of gravity, and it washes off everything that comes in its way. It's a tremendous energy involved there, and that is dangerous, very very dangerous. So what it is a very fast moving liquefied landslide, mixed unconsolidated water and debris. Appearance is like a flowing concrete, and they can occur in the form of a torrent, a drain like a fissure. Then triggering, how they can be triggered? They can be triggered by cloudburst, they can be triggered by earthquake or reservoir drawdown. Now why debris flow? Studying them is important. We need to know that where we are. So I am sitting in Dehradun, suppose, and I am surrounded by the Himalayan thrust system surrounding me. I have very close to me myself, I have MFT, MBT, MCT. So all these are seismically active. Apart from that, there are heavy monsoon and rainfall that occurs in every monsoon season every year, and some of the slopes that are exposed to this, and they are subject to heavy rain. So that basically makes the slope very vulnerable, and that is how any kind of flow, debris flow that happens here, especially the big ones, are to be studied. Now why to model a flow? We have to understand that the evolution of research in landslide till now, what I have described, that has gone beyond hazard zonation. Hazard zonation is something that we have just now learned, but what beyond that? So hazard zonation is okay, my map is with me, but again, as I have told you, my house cannot be shifted, I cannot shift. So somehow a mechanism has to be brought up that so that the risk of damage is reduced in a substantial way. So that is how that will lead to a modeling. So modeling is a priori information based simulation that if you implant on the ground, that can tell you if it happens, how it is going to happen. So what are the effect of it, how much damage it is supposed to bring about, and up to what extent its effect will be, where it will go, does it touch my house. If it touches, then obviously I am going to implant a membrane, a wall before that, so that it doesn't come to my house, and before that only it is digested, the flow is averted, flow is stopped. Now if that is the case, if I have to make a wall, what is the height of that wall, how high the wall should be, because the height of the wall basically is related to the financial constraints. So the more the height, the cost will be more. What will be the width of the wall so that it can digest? For that we need to know how strong, how competent the flow is which is coming down. That's the first point. Second is that it is objective. Whatever hazard zonation, hazard analysis we have done till now, we have learned different algorithms are involved, mathematics based, knowledge based, etc. Different raster layers are involved. They have to be weighted, something like that has to happen in ArcGIS and GIS platform, and then a hazard map comes out. But you go to the field with this hazard map with you, and suppose you go to a field where a place where you should be, theoretically you should be surrounded by all landslide. You are within the red zone, high hazard zone, and unfortunately in the field you see that you do not see any landslide in near about areas. So that simply means from the earth observation, from satellite images, what you have brought out is not completely correct. So why it has come wrong? The incorrectness, the errors can be in the algorithm. You have chosen not chosen the correct algorithm. Maybe you have not chosen the correct layers possible. So where does it lie? So that is how my point is that if you give your layers, your algorithm to somebody else, and they may also come up with a separate map, separate looking map. They use their own layers, they eliminate some layers and get a result which is dissimilar to you. So the subjectivity is involved in every step. But this kind of model, where debris flow model, where my only base is a physics or mathematics, so that basically denies any kind of subjectivity to poke in, and it is completely objective. Third is simulation of natural events of national importance. They are to be done as per the government guidelines. So simulation of events are to be kept ready, so that whenever it happens, we are in a state to know readily what will be its results, the effects. Then unearthing the cohesive factor, prediction of extent of runout zone for future potential flow. Runout zone is something where the whole flow is involved, spatially the spatial coverage of the debris will be your runout zone. Then that is how it strengthens the landslide hazard mitigation as such. We have many case studies to showcase, and some of them lies in India, some of them are outside, some of them in India. Which are those in India? We have taken from Himalaya, we have taken from the Sahyadri Hills, Deccan Basalt South. So all these, there are many. I have jotted down only 5 events, and from these we came to know that whether in different spatial connotation, spatial perspective, my models can work. So and we have seen that we have been quite successful at that, and the model works perfect almost in every condition. So what are the inputs, what are the outputs that you get from that model? First is that you get a height, you get a velocity, you get a momentum and a pressure. These 4 physical parameters along the runout zone where the flow is happening. At any point, any xy you fix, the model will be able to tell you the variation of height, velocity, momentum and pressure. And at that point, suppose your house lies, your school lies. So if the flow has to reach your school, your house, what height it is coming with, what velocity it is coming with, all that priorly, beforehand, before the landslide happening, can be calculated. That's the beauty of this kind of modeling. So estimation of the real cause and validation of how do you validate. Once you get a result, it is to be validated. There are different mechanisms of validating those. I will describe in sometime later. So this is how it looks like. If I map the whole run out, this will be like this. This is the village. Two villages are involved, and the source area is like this, where this flow has started. And another area in Barunabat Parbat. Barunabat is in Uttarkasi, Uttarkasi town in Uttarakhand. And please see how a landslide. This is your simple list for image, a color composite, standard color composite, false color composite, where your infrared has been put in red gun. So that's why all your vegetation is coming as deep red color. You see a trifurcation of the landslide, and in Google Earth, how does it look like? So we tried to take this. This is something that happened in 2001, and today somebody, suppose a student tries to do his own debris flow modeling. So these kind of things, where there is a trifurcation, there is a bifurcation kind of situation happened in past, they have to be taken as case studies, and you have to do hands-on. You have to practically exercise yourself, exercise your modeling capability using those only, case studies only, and see that whether your model results are following this kind of trifurcation, or they are flowing just like that, one direction only. If it is flowing in one direction, something there is wrong in your model. So the moment you understand that your mathematically simulated model follows exactly how it has happened in the nature, my model is perfect. That much of experience is now with you. You can use this knowledge to other landslides where the landslide is yet to happen. It has not happened. It will be a predictive kind of thing. So let us understand the physics behind the heart of the flow modeling, and what are the inputs, outputs. Outputs, I have told you that it is basically the height, velocity, pressure, momentum, all these 4 parameters you get. And we use a frictional law. Why frictional law is there? Because suppose this red block is situated on the slope of theta, and the weight of this red block is mg. If this angle is theta, so mg sin theta is the force that is dragging the material down due to gravity, and opposing this will be my friction. But mind it, the material we are dealing with is a debris, so that simply means it is a mixture of rock and your soil, mixture of rock and water, rock, soil and water. So there are some dry phases, there are some wet phases. So this S is basically that has been fed in the software, that basically is the total friction, this friction. So friction due to a solid phase and friction due to a liquid phase taken together is my total friction. So the total friction is something that is opposing this mg sin theta. But however, the moment the mg sin theta is even equal to or greater than the total friction, the landslide will happen. So that is the physics behind this. So this is how the model understands the landslides, the debris flow to be. And now you know what are the inputs to be given from this equation. So input parameters to the equation, to the software will be, first you have to start with a digital elevation model. So that basically, that is where the base of all simulation run out, on which the 3D GIF kind of thing or 3D simulation lies to be, and it is for representation purpose, for observing purpose. So first is your digital elevation model, but at the same time the digital elevation model, if you are downloading from open source, it has to be of substantially high resolution, spatial resolution I mean. So in this kind of models, it takes around anything above 10 meter spatial resolution of DEM. The software, the results finally that comes out is not good. From our experience, we can tell that anything less than 10 meter spatial resolution will be perfectly okay. Then you need some ortho rectified images, topo maps, just to see the source area. You on the DEM, you basically demarcate the source area, so that basically gives you the x and y parameters of the area, total area is involved, and as because it occurs on a DEM, so from each point it know how much height is involved. So height, average height it knows, and the xy it knows. So basically xyz all you get a volume. If you get a complete volume, Once you get a complete volume, the software calculates how will be my mg sin theta, and based on the topographic parameter, what my total friction is, then there will be a tug of war between these two, and whosoever wins, if the moment friction up till the friction wins, it will be stable, but the moment mg sin theta is more supersedes my total friction, a landslide will happen. So that is the beauty of this kind of simple model. So DEM I have started with, then the auto-rectified images. Auto-rectified images, if it is of substantially good spatial resolution, you will be able to see the cracks of the landslide, that is the proxy that happens on surface. So the cracks basically will let you know how much area is involved, how much area spatially is going to go down. Then your release height, then your frictional values. For calculation of the friction, there are two things: the drive frictional coefficient mu, and viscous coefficient, that is xi. Both are involved. So this mu and xi basically is respectively for your dry phase, that is the rock and soil phase, and xi is for your water phase. Because we have two components, so separate frictions from each of these components has to come. Now this is the source area where the debris flow starts with, and it has to follow this calculation domain, or the entrainment zone we call it. In reality it looks like this. It happened like this. There is a village, you see that some remnant villages are still lying there. Rest of them are washed up, they are completely devastated, they are gone. Now the results of the simulation, how it looks like. Please see this color bar, spatial color graph that represents the model as such, and any point you click, you will get to know about the height, the velocity. So suppose you have your house here, or at the road cross cart, you want to know what the velocity, how much velocity the flow is coming down, that, or what height it is coming down. So that basically you can get to know easily from this kind of output. The software will get you a maximum height versus distance also. So wherever your point is, you can pinpoint that this much of height, this much of momentum or pressure is involved. These are the momentum and the pressure varies. You know, why do I require a momentum? Because the height and the velocity would have been sufficient. It appears so, but believe me, it is not. Because suppose my intention is to implant a dam which basically withstand the thrust of the material that is coming down. So what is the height of that dam or the concrete wall? That will be obviously more than the height, modeled height here, what you get here. But how wide, how strong, you know, at the base the wall is to be inserted for certain distance, certain depth. So what will be this width at the base? So the width basically is function to your momentum, the momentum that the material is coming down, that matters. So that is why momentum and pressure are important. Okay. So I told you about the Uttarkasi, the case study that a student has to take initially, how the trifurcation happens. The results, if I implant again on the Google Earth, where you can see the earlier paths also, you are able to see that how the trifurcation exactly has happened in the model also, and that almost spatially covers what happened in real time. The Kedarnath one, there is a major hue and cry some 1 decade back. Some 1 decade back, and we were also under pressure, tremendous pressure to make out what is happening there. What we understood, what we postulate here is that water was there in the wee hours of 15th and 16th June 2013, but the water was not that much quantity that the devastation will be of this level. So what we postulated is that there are some debris flow that happens here, a kind of landslides that is happening, that is very long, 3-4 kilometer long your debris flow that discharges all its material down here, and the river was coming like this with all water. When it was choked by this, dammed by this, it had to take a path like this. Earlier it was flowing like this. This is the temple. So once choked, So it took another path which is least resistive, and that unfortunately goes through the heart of the Kedarnath town. So that is basically how your Kedarnath was devastated in a major way. And you see how river cutting has happened there. They're all available from satellite images. And it's not that only because of it was choked, it was blocked here, the flow had to come like this. People have found there occurs a paleo channel also within this town, and the water that day would have taken the paleo channel. It was reactivated. That's how the devastation was that much. So on a DEM, in the software on a DEM, you locate your area, then you get another two things, that is your this green border is my calculation domain. So that is something that the operator has to decide. It simply indicates that all my calculation, all my runout will be, once I give this green boundary, it indicates that all my calculation will be restricted within this green zone only. And this violet one is the source area. So that is what from satellite images, from field knowledges, you need to understand how much source area is there, and you have to draw it on the DEM. You have to give the calculation domain. So how do you give the calculation domain? How do I before running the model, I know that this within this much area only the debris will be restricted. Simply we follow, depending upon the strength of the debris flow, how strong it is, how big it is, whether there are some water divides, slope divides. So whether it will cross that divides, can it go to the other side, or it will flow simply like this. So from that idea you get the calculation zone erected. These are the results where velocity, height and momentum of the flow 1 and flow 2 we got, and see the results. Flow 1 was 1.5 kilometers of length, and flow 2 was 2 kilometer length, run out length, and the simulated maximum height was 4 to 6 meter. Velocity was 5 to 7 meter per second. It's quite high. So these all results are published in journals like National Hazards, etc. If people are interested, they can contact me further and to get to read the whole article out. So for two landslides, two debris flows, we tried to model those and got the results. So this I'm coming to the end of this lecture, where I will give you some idea about how to validate the result. One is that simply with the model result, you go to field, you see how physically it has happened, and wherever it is not following the natural path where the debris flow, your devastation is seen visible on ground. If it is not following, then your model is somewhat wrong. You have to correct your model in terms of the algorithm. And another way is that what inputs you give to the software, to the model, is the mu and xi, if you remember the frictional coefficients. So what we do, we go to field, we collect the samples, and we collect the samples in undisturbed state, and at the same saturation level we try to get it analyzed instrumentally in the lab. We have a engineering geology lab where we can analyze, and from the same sample on what I have done my model, the same sample that has been collected from the field, we do the engineering analysis and try to get back the same values mu and xi. So mu and xi is something that we feed the software and see the model. If the model comes out perfect, we stop there, validate the result, we go to field, collect samples, and by analyzing those samples we get another set of mu and xi. So what we get from the instrument mu and xi, and what I have already fed the software for the successful simulation, they are supposed to be at par, they have to be similar, then they are validated. So that's how one type of validation simply indicates that the sample that you have got back shows you how much of xi and mu involved. So that is how we validate this. So coming at the end of this lecture, we basically conclude this and try to understand what happens after simulation. We have seen that the model height, or the momentum, or the velocity that happened in debris flow 1, if you remember in the Kedarnath town, was quite high. to provide sufficient blockade to the main course of the river. There the river is Saraswati. It is basically Mandakini, but upstream we call it Saraswati, and that led to change its course, and consequently the flooding happened of the temple area. It devastated the area. Numerical simulation flow modeling, what we have learned here, can be used for calculation of vital physical parameters to help mitigation. If we have some information about the height, velocity, pressure and momentum, we can get to know, we can think of the perfect remedy for it. So we know beforehand that which are the villages that that may come under the impact of this flow and may get devastated. Shear strength parameter is something that is validated instrumentally, that is used for instrumental validation of the models. Then potential future flows, if you model one flow, and then if the geology, if the frictional parameters, the rock types, because that do not change very frequently. So in the nearby areas also, with the same input values, you can try your own models, and as because the inputs remains almost similar. We can do change detection in case of repeated flows. So suppose the big landslide where there are a number of landslides, every rainy season there is happening, there is the incidence of landslide. So if you have a model ready, and from satellite images or from your field visits, you can get to know that this year the crack has progressed this much, this is the new area that is especially this is that is going to get dislodged. If this information is there, you can run your model. Old model can be updated, and you get newer updation every year, and your simulation one time you do, and that works for suppose a decade. So that is how. Thank you. At the end of the lecture, I would like to tell you that we have been engaged in this business for landslide. We have been engaged in the research of landslide for last 10 years for myself and my group that is working there for last 25-30 years. And from this I can assure people, I really want to tell people that do not demonize landslides. Landslides are not demon. So they are a natural process, like your earthquake, like your volcanoes. So they are natural process. Then the nature basically tries to make the equilibrium by adjusting its slope. So like in universe, we have to maintain the perfect entropy, right? So the slope also same way it tries to maintain the perfect equilibrium. That's why they keep on happening. So don't demonize them. Rather, you please understand, try to get their pulses, their vital statistics, what they are trying to say. Not many people have done, still working. It has become an active area of research. We try to catch it using remote sensing, satellite images, etc., satellite derived products. But to me, if you see it, there are only 5 things that is important: the topography, the lithology, the rock type, the structure, the trigger mechanism, and the pore water pressure. These 5 things are basically like your pulses, BP, etc., that is happening in your body, and doctor checks and tell you how you are. So these 5 things, if you can get from the slope, from the landslide, basically you understand its emotion of the landslide. So with this, I